Hi, everyone. We're going to get started. So welcome to the last webinar of our Spring 2021 series. As a reminder to change your displayed name to your name, comma, university or company, and that just makes it easier during the Q&A session to call on you. For those of you that don't know me, my name is Kelly Baber, and I'm the Energy Systems Engineer at Rutgers University Case. Just a reminder to keep your computer or phone muted throughout the webinar. There will be a Q&A session at the end. So if you have any questions during the presentation, feel free to put them in the chat and we will address them at the end. This webinar will be about 45 minutes long and followed by a 15-minute Q&A. On to today's topic, specifying fans for industrial environments, presented by AMCA. And I will pass it over to Lisa, who I'd like to thank for helping coordinate this webinar. And welcome our presenters, Dan, Marcel, and Aaron. Lisa, you should be
Hi,
able
Kelly.
to share.
Great. Hi. Thank you. Let me pull up the presentation here. Okay. And hopefully you all can see the main slide for our presentation today.
Yes,
definitely, we want to thank Kelly and Rutgers for the invitation to speak with you all today. We've done a couple of these with them, and it's always a wonderful experience, hopefully on both sides. So today's title is Specifying Fans for Industrial Environments. I am Lisa Cherney, the Education Manager for AMCA International. And just a few little housekeeping notes that we need to go through. As some of you or all of you may be aware, we are making professional development hour credit available, 1 credit hour for this program. We issue those through our CEP, Registered Continuing Education Program, of which we are an authorized member. Do have to mention that our CEP does not approve or endorse any content of this program. And in order to achieve the professional development hour credit, you do need to stay on the program for the entire broadcast, and please complete a survey. The link will be sent to you in the chat, and you can complete that after today's program. A quick disclaimer that the information we are about to present is for educational purposes only, not intended to serve as professional engineering or manufacturing advice, and the views being expressed by our presenters are theirs alone and do not necessarily represent the views of AMCA. In making this activity available, we are not endorsing, sponsoring, or recommending any particular company, product, or application, and AMCA International shall not be liable under any circumstances, including negligence, for any damages arising out of a party's reliance upon or use of the content contained within this program. The materials are copyrighted, so any unauthorized use or reproduction is prohibited. However, I will let you know that following the program, Kelly will be posting the PDF version of this presentation on the website, so you can look for that shortly. Very quickly, we have some learning objectives here. Our goal is to provide information on key environmental, aerodynamic, and mechanical aspects of industrial fan performance today. And by the end of the presentation, you should be able to describe how industrial fans differ from commercial, define the different forms of pressure and flow, calculate density, compare centrifugal and axial impeller designs and how they impact fan pressure and efficiency, as well as explain key considerations for selecting fans for abrasive, corrosive, and high temperature environments. And with that, I would be very pleased to introduce to you our 3 presenters today. One of our presenters, Aaron Saldana, is a sales director of industrial fans for one of our AMCA member companies. He has worked for over 13 years for leading fan companies in the US and India. He has experience in engineering management, sales, production, quality, and new product development, and he is a member of multiple AMCA and ASHRAE committees. Our second presenter is Marcel Komutsky. He's the Vice President of Engineering and Automation for one of our member companies. Marcel has 30 years in custom fan manufacturing, and he obviously is the current VP of Engineering and Design Automation. He's a professional engineer registered in the province of Ontario, Canada, and his experiences included in-house software and development, design engineering, and sales applications engineering for large multinational fan manufacturers. And our third presenter is Dan Horman. He is the engineering manager for another AMCA member company. And FYI, no, all three of them do not work at the same company. So they bring extra knowledge and extra valuable perspective because of their independent experiences. Dan has designed custom heavy-duty fans for utilities, mining, pulp and paper, tunnel emergency ventilation, and oil and gas industries since 2012. He served 8 years in the U.S. Army Reserve and has a Bachelor of Science in Mechanical Engineering from North Dakota State University. And a little inside joke for the audience is during the rehearsal we did the other day, I inaccurately said he was from South Dakota State University. So my apologies. I definitely don't want to offend any university loyalists. So with that, I would like to turn the program over to Dan.
Thank you, Lisa. Good to see that's corrected on there. So let's see, hopefully I got control here. Let's do a quick check. I do, good. All right, so today I will be discussing some of the differences between commercial and industrial fans. So there's no line in the sand as far as when fans are classified as commercial or industrial. Industrial fans are generally larger for a given speed or have higher blade tip speeds. Industrial fans are typically designed for higher pressures, but high flow, low pressure industrial fans are possible, but are generally larger, higher horsepower. Commercial fans will vary, from fractional horsepower all the way up to maybe 100 horsepower for a large building HVAC system. But industrial fans, there is some overlap. They will be, in the 10 to 20 horsepower range, all the way up to 10,000 horsepower for like a utility FDID fan, FD or ID fan. So industrial fans, they vary in size, shape, and features. Ultimately, many of the features found in industrial fans exist for the purpose of increased reliability. For many of our customers, downtime and unexpected outages can be very costly. So there we go. So the first, let's see here. Okay. I thought there was another slide. Well, so I guess the first noticeable feature of industrial fans is that they look heavier. Thicker plate gauges are stiffer, and they typically have more reinforcement. Natural frequencies are shifted outside of the operating range of the fan on the fan housing and impeller. Shafting on industrial fans is also generally larger for critical speed separation or natural frequency separation. Critical speed is the term we use for the natural frequency of the fan shaft. Thicker plate also allows for some corrosion resistance or corrosion allowance before any structural integrity is lost. Sometimes duplex nickel alloys are used on industrial fans for increased corrosion resistance, more so than just a stainless steel, for example. Continuous welding is also more common on industrial fans to prevent the possibility of water ingress. Skip welds can allow water to penetrate the unwelded portion. Sometimes caulking is used to seal that skip weld, but that can deteriorate over time. So kind of the middle there, you see an example of a skip weld where water has obviously begun to penetrate, and you're seeing rust bleed from that weld. No, it'll change. There we go. So, oh, too far. All right. So the commercial fans typically feature ball bearings. Ball bearings can operate at higher speeds, but have lower load capacity. Industrial fans typically feature spherical roller bearings. Since the rollers make a line contact rather than a point contact, they can accept higher radial and thrust loads compared to a ball bearing. These bearings are often referred to as self-aligning bearings. The spherical rollers themselves and the inner outer races allow for the inner race to pivot with respect to the outer race without impacting the bearing life. Generally, the misalignment is ultimately dictated by the seals that are in the bearing housing. Ball bearings can experience premature failure if the rolling element is incorrectly seated in the bearing housing. This is more common on ball bearings. And if it's incorrectly seated, that's going to result in increased vibration. So, you know, the majority of fans below 1,000 horsepower are going to have roller bearings. This is kind of another point where there's not really a fixed line as far as when we switch from roller bearings to hydrodynamic bearings. You could say generally maybe about 1,000 horsepower fans feature hydrodynamic bearings, kind of pictured on the bottom left there. But you know, this is somewhat of an owner preference on which type of bearing they want to see in their fan. In sleeve bearings, the fan shaft runs on a thin film of oil, and there's no metal-to-metal contact. The bearing only experiences wear during startup and shutdown when that oil film was actually lost. So during normal operation, the bearings virtually have unlimited life since there is no metal-to-metal contact. The sleeve bearing life is ultimately reduced by the number of starts and stops if there's oil contamination or any sort of excessive vibration in the fan. Sleeve bearings generate more heat than roller bearings, so oftentimes these bearings require some external cooling, whether it's water cooling or oil cooling. They also have a lower temperature limit because of the babbitt material in the liner of the bearing. So industrial fans are subject to lower acceptable vibration limits as compared to commercial. AMCA 204 is a standard relating to allowable vibration in fans. So it provides categories based on fans' purpose and size. Each of these categories have an acceptable factory and field vibration levels. Industrial fans generally fall into the BV3 or BV4 category. And a lot of features or many features in industrial fans exist with the purpose of reducing vibration. Lower vibration ultimately results in less fatigue and improved bearing life. So AMCA 204 provides recommended alarm and trip levels as well. These can be used to schedule maintenance before an unexpected outage or failure were to occur. So while direct drive, fans are becoming more common in the commercial side of fans, the majority of industrial fans are direct drive or have been direct drive for quite some time. So direct drive fans are ones that utilize a coupling to connect the fan shaft and the motor shaft, and they allow for some misalignment, or the coupling is able to accommodate that. Belt drive fans allow for either slowing or speeding or changing the speed of the fan by selecting different belt drive ratios. The direct drive fans, on the other hand, are going to run at the speed of the motor. So they either have to be custom sized to hit their specific duty point, or they need to use a variable frequency drive to change the speed of the motor, or a damper, or some other means to meet the required performance. So there are some drawbacks to belt drives. Belt drives can wear and require more frequent maintenance as compared to most direct drive couplings. Belt drives also typically exhibit higher vibration due to the belt pass frequency. So there are imperfections in the belts, which as that imperfection passes over the sheave or the pulley, a radial force is exhibited, resulting in vibration. Belt drives also require tension to operate, and that belt tension or belt pull applies additional load on the fan and motor bearings, and that can decrease the life of those bearings. So industrial fans typically feature continuous monitoring. So some of the things that are monitored would be like the motor winding temperatures. They're monitored to protect the motor from overheating, or allow the operator to adjust the operating conditions before any damage occurs. Sometimes fans are designed to operate at higher temperatures. If it's run at an ambient air temperature, that may result in the shaft horsepower exceeding the motor's rated nameplate horsepower and overheating of the motor. Bearing temperatures, they're also monitored to prevent any overheating or indicate maybe a loss of lubrication. Bearing vibration is monitored to indicate, a host of possible mechanical issues, including, looseness, possibly material buildup on the fan, if there's dust loading or something moving through the fan that has the potential for buildup, or give some advance notice of upcoming failure, seeing an increase trend of increasing vibration. Seismic transmitters, as pictured on the very right there, are common for roller bearings, but for hydrodynamic bearings, the shaft rides on an oil film, which allows the shaft to vibrate somewhat independently of the bearing housing, or at a different amplitude. So on these sleeve bearings, typically proximity probes are used instead. That's what's pictured on the bottom there. So the proximity probes don't actually make contact with the shaft. They maintain a gap, but they're able to measure the shaft vibration due to its relative proximity. Also on industrial fans, preventative maintenance is certainly more common. There's more inspections and checks. Preventative maintenance might include bearing FFT analysis, looking at the vibration spectrum of the bearing to detect potential bearing faults or defects, and as well periodic, inspections of the fan impeller for fatigue or cracks are more common on industrial fans for sure. So there's three common arrangements for industrial fans. So the first one here I'm going to talk about is arrangement 8. And commercial fans, you might see some that look similar to this, but typically those have the motor mounted directly onto the impeller directly mounted onto the motor. In an arrangement 8 fan, the impeller is mounted on its own independent fan shaft with independent fan bearings. This extends the life of the motor, since these bearings are generally roller bearings versus the ball bearings in the motor. The fan impeller is overhung on the fan shaft, which allows for a round duct which is perpendicular to the inlet of the fan discharge. So the air sort of takes a 90-degree turn going through the fan. So this arrangement is more common on the smaller size end of industrial fans. Certainly many fans under 100 horsepower will look something like this. Moving on, arrangement 7 will look similar to, or somewhat similar to arrangement 8, but the main difference is that the impeller is center hung between the fan bearings. This allows for larger shaft diameters and better critical speed or natural frequency separation, because the diameter of the shaft can be increased in the center. It can be stepped up from where the bearings are at. With arrangement 7 fans, they generally require an inlet box, which you kind of see on the right side there, those inlet boxes that are facing up. The inlet box and the discharge ducts will be parallel, so there won't be a 90-degree turn in the airflow like you would see on an arrangement 8. Arrangement 7 fans can also be designed with double inlets. Kind of what you see there on the bottom left is that that's a double width fan that'll receive air from both sides of that impeller. Double width fans are more suited for higher flow, lower pressure applications. Fan bearings in this arrangement are mounted on independent pedestals, independent of the housing. This helps avoid any aerodynamic vibration being transmitted to the bearings. Lower vibration obviously just results in increased bearing life and reliability. So that's why that's done. Let's see here. So arrangement 7 and arrangement 8 fans can also be supplied with inertia bases. Inertia bases use springs to isolate the structure or whatever the fan is sitting on from the fan, and I also isolate the structure from any vibration from the fan. Now, on some commercial fans, you'll see what I would call an isolation base. The difference between these two, isolation and inertia base, is that the inertia base contains concrete. The concrete improves the base stiffness as well as natural frequency separation. So in the bottom of the base of the fan, it'll be filled with concrete. A heavier base results in a greater static to rotating mass ratio. The greater this ratio, the less response to any impeller imbalance there is. In general, you'll see different recommendations. Somewhere between a 4-to-1 or a 7-to-1, depending on who you ask, will be recommended as far as a rotating mass to, or sorry, a static mass to rotating mass ratio. So the static mass or the concrete mass will be, say, 5 times the mass of the rotating element. And that's obviously to improve the stiffness, and then as well reduce the response to vibration. So lastly, in the arrangements is for industrial fans is the arrangement 3. Arrangement 3 fans have center hung impellers similar to the arrangement 8 or similar to the arrangement 7, but the motor and bearing pedestals are concrete rather than steel. This arrangement is most common on fans greater than 1,000 horsepower or so. There's not a fine line in the sand, but certainly on the larger multiple thousand horsepower fans, this is the common arrangement. The concrete pedestals, they provide superior bearing stiffness, support stiffness. Heavy concrete pedestals have a high static to rotating mass ratio, thus they reduce the impeller response. A fan with a large static to rotating mass ratio, again, will be less sensitive to imbalance. Ultimately, lower vibration and increased bearing life is the goal here and what's expected out of this arrangement. So lastly, and one more feature on industrial fans would be that they commonly feature machine surfaces for mounting of the fan bearings and motors. You won't necessarily see this on commercial fans. So unlevel mounting surfaces can result in a motor softfoot. A motor softfoot is distortion of the motor frame when it's bolted to an unlevel pedestal or subbase. That distortion of the frame can result in a negative impact of the motor air gap and reduce the motor life. Fan bearing mounted on a non-flat surface is also problematic. If the surface is concave or convex, that can result in distortion of the bearing housing. A distorted bearing housing can pinch the bearing element itself and result in increased vibration and decreased life from that as well. Bolting the motor and bearing bearings to non-flat surfaces can also result in pointer line contacts rather than a surface contact. A pointer line contact between two flat surfaces, that line or point can wear over time due to vibration and then ultimately result in more looseness and vibration. That point will wear down. Machine surfaces also improve the ease of coupling alignment in direct drive applications. If the motor and fan bearings are mounting surfaces are not parallel, the fan and motor shafts will have a vertical angular misalignment. This misalignment can be difficult to correct and requires the use of taper shims or step shims. And similar to having a pointer line contact, those step shims have the possibility of loosening over time, and they can result in increased vibration. And I guess with that, I'll probably turn it over to Marcel here.
All right, good afternoon, everyone. My name is Marcel Kaminsky, and I'll be talking with you this afternoon about the aerodynamics of industrial fans. We're going to cover a few different things today, and I'll get through this without putting as few of you to sleep as possible. But we're going to be looking at pressure and flow definitions. We'll be looking at something called static pressure regain. We'll also spend a bit of time calculating density and why that's important. We'll look at system losses and system curves and how system curves interact with the fan curve. We'll cover a concept called specific speed, which can be very important. We'll also touch briefly on the fan laws to give you a sense of how they work. And then we'll look at the performance of various blade shapes, primarily of centrifugal fans, but we'll also touch on some axial fans. There we go. All right, so looking at AMCA 99, we've got some basic definitions. I'll go over this quickly because you will get the PDF. You can go over this in more detail yourself later, but pressure is essentially a force per unit area, whether it's PSI, and in fans, we typically look at inches water gauge or inches water column, and in other parts of the world, they'll look at pascals or kilopascals. Now, there's a couple of types of pressure we're going to cover. Absolute pressure is the value of a pressure when the datum is absolute zero, and a barometric pressure is an absolute pressure that we experience at the location of measurement, typically 14.7 psi, 14.7 psi at sea level. Gauge pressure is what we typically look at in the fan industry, and that's the differential pressure between a reference pressure, such as a barometric pressure, and the absolute pressure at the point of measurement, and it can be positive or negative. All right. Sorry, I'm having some trouble with the controls. It worked earlier. Static pressure is a pressure that exists by degree of compression only, and it can be expressed as a gauge pressure, and it can be positive or negative. Think of a balloon and the pressure that keeps the balloon inflated. That would be a static pressure. Velocity pressure exists by virtue of rate of motion. So again, just picture your arm out the window of a moving vehicle, and that force on your arm is essentially a form of velocity pressure. And then the total pressure is the algebraic sum of the two at a point of measurement. AMCA defines 3 types of pressure that are typically used to define how a fan is rated. There's fan total pressure, which is the difference between the total pressure at the outlet and the total pressure at the inlet. This is typically used for axial fans and is often used in fans that are rated and specified in Europe and other parts of the world. Here in North America, though, we typically look at either fan static pressure, which is the static pressure at the outlet minus the total pressure at the inlet. Something like that would be, Dan talked earlier about forced draft fans. It could also be used for fresh air supply, air handling units, anything that's taking air from a point of rest to a point of motion. And then the third typical fan definition is static pressure rise. And that's the difference in static pressure between the fan inlet and the outlet. And that's typically used for induced draft fans or some other process where the gas is already moving and the fan's role is, in this case, simply to increase the pressure of the gas so that it can do useful work through the rest of the system. Here's a quick outline of what the different pressure points are at the fan inlet and the fan outlet. And you can see that graphically how the different pressures can be listed and how they can also give it a different total value. And so it can affect fan sizing. We touched earlier on something called static pressure regain. And that essentially is something where a fan will have a fairly high velocity at the fan outlet and it has a high velocity pressure, but the pressure required to do work through the system is static pressure. And so regain lets the flow expand and slow down, and some of the velocity pressure gets converted to static pressure so that it can do useful work through the system. All right, and most fans in North America are rated on static pressure. And here's just a quick definition again from AMCA 801 that's defining the inlet and the outlet planes of the fan system, 1 and 2. In this case, it includes a silencer and a vase, as well as an inlet box and a transition. Other times it may or may not. So it's important for the user, the end user, and the fan manufacturer to agree on what are the planes. A fan, we often talk about actual volume flow rate. A fan is a constant volume device in the sense that a fan of a given size running at a certain speed will always produce the same volume flow rate. The pressure it creates and the power it draws will vary, but the volume flow rate will be the same. There's also some other flow rates that are defined that are useful for system designers because it eases sizing components. There's standard flow rate, which is common in North America, and normal flow rate, which is common in Europe and other parts of the world. And then there's mass flow rate, which normal flow rate and standard flow rate, excuse me, can also be expressed as a mass flow rate. And this is important because most systems that use fans are actually mass flow based, whether it's a cooling application or an industrial process. They're all based on a certain amount of mass flow for the process to work properly. I've got a couple of examples here of how density is calculated. We'll look at the inch-pound option here, and density at 70 degrees Fahrenheit at sea level is approximately 0.075 pounds per cubic foot. And then it can be corrected for temperature barometric pressure, which is P, and also the molecular weight of the gas being moved. I'm going to speed it up a little bit here. So basically speaking, the molecular weight of dry air is 28.964, and water has a lower molecular weight. So if you have moist air, the air will be less dense because each water molecule will displace one molecule of air. And so the net effect of that mixture is that the molecular weight will be reduced. We also have some concepts here of standard air and normal air, and these relate back to the standard flow rates and the normal flow rates. But why is density so important? Well, recall that a fan is a constant volume device. And as I said, most applications that use fans are based on mass flow, whether it's combustion air for burners, cooling air for coils, or even petrochemical processes. They all depend on a certain mass flow for proper operation. And you can see that with, in this case, when the pressure doubles, the amount of, or when the density doubles, the pressure that the fan creates also doubles. And then just one quick example. If, for example, a system was designed at 36,000 CFM at standard flow rate, and now it was installed somewhere else, say in Denver or some high elevation where the density is reduced, in order to get the same mass flow rate, the volume flow rate has to increase to 45,000 CFM. So quite a big increase in flow. In addition, the system resistance drops through the curve, through the system. However, there is much more flow, so the total pressure actually increases as well. And so the fan ends up having to be much larger just to produce the same mass flow at a lower density. All right, so flow is created through a system by increasing the pressure, and then that pressure forces the flow from the high pressure side to the low pressure side. And then each system is comprised of different things. There's flow control devices, there's reactors and other furnaces and other devices that use the flow for the process. But most system losses tend to vary as a square of the flow rate. If you double the flow, your system loss will be 4 times higher. And here's an example. If we're increasing the flow by 20%, the system pressure drop will increase 44%. And then there's also, that's system A. But if we look at system B, which has a higher system resistance, overall the flows will be much less. And then system C has a lower system resistance, and the flows can be much higher for a given pressure drop. But why is this important? Well, a fan will produce any flow along its curve, anywhere from full shutoff high pressure all the way to full open and low pressure. Where it operates in a specific system is where that pressure curve, the fan pressure curve, intersects the system resistance curve. And so that we call that the operating point or the system design point. And that's also why systems designers often will overestimate the system resistance, so that if there is an error, rather than moving to the left of the curve in a possibly unstable area on the left here, it will move to the right of the curve and still be in a stable operating point. Continuity requires that the flow through a system, assuming there's no leaks or additions, will be equal at any point. And so we can see that as the duct size increases, the velocity will decrease. And so system pressure drop through lower velocity will also be lower. I touched one thing we want to look at very quickly, but it's important, is a concept called specific speed. And this is the formula we use here in North America. And it basically gives an idea of where is the fan, or what is the specific speed of the system operating point. You know, we know the required flow and we know the required pressure, and then we can pick a different operating speed and before we select any fans. And that will give us an idea as fan manufacturers, which fan might be best suited for that application. We can see here that pressure blowers, they have a low specific speed and fairly low efficiency. And axial fans will have a high specific speed and also very good efficiency. And in between, there's different types of centrifugal fans, whether it's a wide centrifugal fan or not quite as wide, or a very narrow pressure blower. But each of these values can be calculated for the specified flow and pressure, and then that gives the manufacturer an idea of which fan might be best suited. We also want to look at fan laws, and the fan laws allow a fan, well, first of all, they allow a fan to be resized for a different application, either by changing the speed. If there's an existing fan, you can't really change diameter very easily, but you can change the speed, and that will let you know what the new operating point might be at a different speed. But fan manufacturers have what we call unit curves, and then use that unit curve and the specific speed to decide how big and how fast the fan needs to run to achieve the required performance. And so these laws, these rules allow the manufacturer to estimate what that size will be. We call them fan laws, but they apply as well, equally well in the pump application. The only difference is that pumps are typically incompressible fluid flow, and industrial fans are typically, but not always, but typically a compressible flow. The laws as detailed here don't include the compressibility coefficients, but in the AMCA 99 details, it's all spelled out quite clearly there. All right, so some different impeller designs. We'll start with centrifugal fans, and the most efficient option is an airfoil. There's different shapes, but they try and mimic the airfoil of airplane wings, and they move the air very efficiently. They can be high pressure, but they are better suited for relatively clean flow so that that they don't wear unevenly. There's a risk that if it wears unevenly, that the impeller is hollow and it can start to fill up with dirt and get imbalanced. They also have what is called a non-overloading characteristic, and that is that the fan power will have a peak power. And so it's possible to select a motor size that will make sure that no matter where the fan operates, it won't overload the motor. Similarly, backward inclined and backward curved fans also are non-overloading, but they're not quite as efficient as an airfoil, but they can be better suited for dirtier applications. They're fairly easy to protect. Similarly, radial bladed fans are, well, they're just what they say. The blades are straight radial. They're essentially like a paddle wheel, and they're good for, they tend to be good for high pressure applications, but they are a continuously rising power characteristic. So you need to be careful in sizing the fan and the motor. And then a modified radial or a radial tip is radial at the tip of the impeller and backward inclined at the inlet. So it has a slightly improved efficiency over a plain radial blower. And it's also what's called self-cleaning. There's very little buildup on those fans. And then forward curve fans, they're not so common anymore in industrial applications. They're more common in furnace fans, that sort of thing. But in the past, they were used for induced draft applications because they do provide a high flow at a low pressure, and they're slow operating speed, and they're fairly quiet. So they do have still many good uses. Also, some axial fans. We have what we call a tube axial fan, and it can be any kind of impeller blade, but essentially it's an axial fan impeller mounted on a motor or shaft, and the flow exits axially, but has a high rotation component. I guess I should clarify, a centrifugal fan, the flow enters the impeller axially and leaves radially, and an axial fan, the impeller or the flow enters the fan axially and then also leaves axially. And then a vane axial fan compared to a tube axial is very similar. The difference is that there's fixed guide vanes added, which reduce the swirl component, and they can increase pressure capacity of a similar impeller by almost 20% in some cases. All right, and with that, I'll turn that over to Aaron. Thank you very much for your time.
Good afternoon, folks. I'm Aaron Saldana, the Director of Sales at Howden. In the interest of time, I'm going to go a little quick, but feel free to reach out to any of us post the session if you have questions. So let me just make sure, yeah, it works. Okay, cool. Today I'm going to talk you through the design considerations when we build fans for special environments like abrasive, corrosive, and high temperature environments. So first off, we have fans for the abrasive environments. In the fan industry, we define an abrasive environment as one where the particles in the airstream cause the wearing away of the fan surface by friction. This typically happens at the blades and scroll of the housing. Some applications where we see high abrasion in centrifugal fans are in the cement industry, in the iron and steel industry, with dust collectors, and in coal power plants. On axial fans, the main areas where we come across this kind of abrasion is in mining and in coal power plants. So as fan manufacturers, we first need to predict where the wear will occur, which is a function of the dust particle size and the type of fan selected. We then need to look at to design those areas to either minimize the wear or withstand the wear. With regard to minimizing wear, we typically try to use higher efficiency fans like backward curved or backward inclined fans. I will go into the why a little later in the presentation. We also look to use wear deflectors and try to select fans that operate at slow speeds. With regard to withstanding wear, we look to either increase component thicknesses or use wear protection devices. Typically, we use a combination of both of these techniques. So looking at the precautions to be taken, on the right side, you will see the various coatings and wear protection options that are available for both the wheel and the scroll of the housing. On axial fans, the way to deal with wear depends on the magnitude of wear you see. So one of the ways with the aluminum bladed fans is to use a wear protection on the leading edge of the blade, or the other option is to build a complete axial blade out of SGI. One important note is that all accessories in the airstream also need to be prepared for this wear. Next, we'll go into material selection. So you can see, like, if you look at erosion versus life of the fan, you'll see that conformer clad is clearly the most impactful, has a longest life in an abrasive environment, but it's also the most expensive. You're looking at 14x the cost. So it comes down to the commercial viability and feasibility of a project. What does the customer hold important to them? Is it first cost or is it long life? The other thing to note is the way we overlay wheels with this hard-facing material. It is never put directly onto the blade. There's always an intermediate material put there. So this allows us to change the wear liners as needed. Another way to reduce erosion is to select a slower fan. A slower fan means a larger fan, which often leads to higher first costs. In the long run, this might be advantageous, as reducing the speed by half would reduce the erosion by a factor of 8. As mentioned earlier, using high efficiency designs such as backward curved or backward inclined wheels would reduce the operation costs. Since these wheels are higher efficiency, the airflow through the wheels are smooth, and the possibility of dust accumulating in the dead airflow zones are much lower. When dust does accumulate here, it causes excessive vibration and which leads to bearing failure and ultimately wheel failure. Moving on to fans for corrosive environments. We define a fan in a we define a corrosive environment as one where there is the gradual destruction of material of construction of the fan due to a reaction with the chemical or electrochemical airstream. We typically come across these requirements in petrochemical plants or chemical processing, fertilizers, wastewater treatment, etc. As a point of reference, the direct cost of corrosion in the US is approximately $276 billion a year across all industries. So what do we look for when we design these fans? We first need to understand if only the airstream gases are corrosive, that is the air going through the fan, or if the fan is placed in an environment that is corrosive. So if the fan has to be designed only for a corrosive airstream and not external environment, we then look to see if the gas is only corrosive or if it is flammable and hazardous. The reason for this is if it is flammable, we would need to consider an anti-sparking device. If it is hazardous, we would need to consider a low leak design. When it comes to material, as I mentioned earlier, we look to either select the base material to be corrosion resistant, or we look at coatings. When selecting the base material, it comes down to the chemicals in the airstream, the size of the fan, and the stresses in the fan. We can either use materials like stainless steel, Hastelloy, special alloys, or on smaller fans, we can use composites. These composites are specifically designed to combat corrosion. The downside is they typically have higher first costs. An alternative method is when there is a cost constraint, you typically go in for some kind of a coating. So looking at spark proofing, in cases where there is a flammable airstream, AMCA standard 99 provides guidance on the construction. So starting at the bottom, C is the least stringent, A is the most stringent. I'm not going to go into this in interest of time, but this data is available for you to review later. So this example is where a customer specified a stainless steel housing for a nitric acid application, but they wanted to save on costs and not put in a robust seal. So what happened was the nitric acid escaped from the back of the fan, got onto the bearings, and the bearings were damaged. So this is the fan by adding a labyrinth seal onto it. So this is the way a low leak construction can improve the life of your fan. So moving on to fans for high temperature applications. So in the fan industry, we define a high temperature environment as one where the airstream temperature is 300 degrees Fahrenheit or higher. We typically come across these applications in petrochemical processing, forced draft circulation, etc. I'll point out in HVAC applications, we typically see high temperature requirements there, but that is for specific durations of less than 2 hours, which is mainly for fire safety. So basically those fans should work in case of a fire and last through 2 hours of the fire. So coming to the design of these fans, we first need to select the airstream materials that are suitable for the operating temperature. On the right side, you will see the materials. You'll notice that as you go above 1500 degrees Fahrenheit, the cost of the material substantially goes up. One of the things to note on axial fans is that the tip gap is very important when it comes to high temperature applications, because there will be expansion of the wheel, and if that gap is too small, the wheel will potentially hit the housing. So features of high temperature fans. So the first thing is these will have a cooling wheel to cool the bearings, as you can see here. You will have some studs on the housing. This is so that you can put an insulation jacket on top of the fan. You will see a raised access door to accommodate that insulation jacket. On the right, you'll see a double jacketed design. This is a lot more expensive, but also a lot more efficient. At the top, you will see some of the precautions we take with design of the shaft. So if you're looking at fans of between 1500 degrees and 1800 degrees, we typically use a hollow shaft which allows for air to circulate within the shaft and cool it. For temperatures above 1800 degrees, we typically use a hollow shaft, which has water circulating through the shaft to cool it. This is an example of a fan that has been designed for both high temperature and corrosive environments. So you'll see that it has an Inconel wheel, a stainless steel housing. You'll notice that it's got extremely thick flanges to reduce leakage. You'll also see that the gap between the holes are very small. This is also to reduce leakage. You'll see a monoblock bearing. You'll see that the base is machined for the motor. So these are some of the precautions we take for high temperature fans. I know that this was a lot of information to digest in a relatively short period. So feel free to reach out to us if you have questions or need further information. Thank you for your time. Back to you, Kelly.
Thank you everyone for your presentation. We're now opening it up for questions. So if you have a question, just unmute yourself and ask, or you can put it in the chat and I will read it aloud. Question from the chat. Can you share some telltale signs of an industrial fan not operating at its optimal efficiency?
Marcel, do you want to get that or Dan?
Um, it's difficult to say, but there are, I guess, well, some telltale signs. If there's a lot of noise, then perhaps the system resistance is higher than expected. And so the fan could be operating to the left of the peak point of the curve. And so it's maybe in an unstable operating area. And similarly, if the system resistance is underestimated or overestimated and the fan is operating far to the right, it could be that there's so much flow going through the system that either the system ductwork is vibrating a lot, or perhaps the dampers need to be closed a fair bit to maintain power limits. And so then there's just going to be a lot of turbulence inside the fan, which will also generate noise. Thank you for the question.
I was going to add one thing we commonly see, not necessarily that the fan is operating inefficiently, maybe that the fan wasn't selected properly, or that the system resistance is much less than expected. So what happens is the fan is normally operated, if it has dampers, operating with the dampers at 30% open, and that results in very inefficient operation. Sometimes what happens is, as the system is being designed, extra margin is added on to extra margin, and the fan ends up being oversized, and to get to the required performance, it's dampered, and that results in inefficient operation.
Right, thank you. Another question from the chat. Can you comment on the efficiency of different fan capacity control methods?
So there are multiple methods to control the capacity of the fan. Probably today the most efficient is through a VFD control, that is through varying the speed of the fan. In the past, you used to have variable pitch guide vanes for centrifugal fans, where you could adjust the pitch of the inlet control vane to adjust flow and pressure. Another method for axial is through adjusting the pitch of the blades itself. Again, speed control is the most efficient, but these are other methods, through a damper, through adjusting the pitch of an axial fan, or through an IBC.
All right, thanks. So we did run over a little bit. Does anyone have one more question? And I am putting my email in the chat. So if anyone thinks of any more, they can email me and I will forward it on to our presenters.
Yeah, I've got one real quick. We just mentioned variable pitch control on axial fans. I've heard that they have high maintenance requirements, and that while the efficiency is good, the long-term cost of maintaining them is relatively high. Is that true?
That is true. The fan itself is a lot more expensive than a standard fixed pitch axial fan. So there are a lot more moving parts. So obviously your maintenance is going to go up. Again, having said that, you're looking at typically those fans are super robust. You're looking at least a 10-year life on them anyway. So again, if you're looking at efficiency, speed control is the way to go.
Thank you.
Yeah, I'd agree. Speed control VFDs with advancements in VFDs that have been made in the past decades. There's less issues with VFDs, so people are more apt to go that route.
All right. Thank you to Lisa, Aaron, Dan, and Marcel. My email's in the chat, so if anyone has any more questions, just email them to me and I will forward them along. Thanks for the presentation.
Thank
All
you,
right, thank you,
Kelly.
Thank you,
Kelly.
Kelly.
Everyone.
Bye.
And thank you, everyone, for your time today.